Hello guys, so today we are going to discuss the first topic of the chapter magnetism, and the topic is the current loop as a magnetic dipole. Current loop as a magnetic dipole. Okay, let us consider we have a circular current loop. Okay, so we can take this as a circular current loop having the direction of the current anti-clockwise. Current I is flowing in anti-clockwise direction, and O is the center of the circular loop, and R as the radius of the circular loop. Okay, so this is the cross-sectional view, means the loop is currently lying in the plane of the board. Now if we take its side view, so we can draw it as in this way. Okay, and the current is flowing in anti-clockwise direction, so the direction will be represented as in this way. Okay, this is the center O. Now as you know, in the previous chapter we have calculated the magnetic field due to the circular current loop at a point P at distance x from the center of the loop. Let us consider this is the point P, which is situated at distance x from the center of the loop, and this is the radius R of the loop. So magnetic field at point P is given as B is equal to mu naught I R square over 2 R square plus x square whole raised to the power 3 by 2. Okay, this is the expression for the magnetic field at point P, which is separated at x distance from the center of the loop. So if the point x is lying far away from the center of the loop, means if x is greater and greater than R, if x is greater and greater than R, we can neglect this term R square. So it will become B is equal to mu naught I R square. We will remove R square only in denominator, not in the numerator. So it will become mu naught I R square to x square whole raised to the power 3 by 2. Now here 2 and 2, these will cut each other, and it will become 2 over x raised to the power 3, 2x raised to the power 3. Okay, so this is the expression for the magnetic field at point P, which is at a large distance x from the center of the loop. Now, so this is the expression for the magnetic field. Okay, now if we multiply this whole term by 4 pi divided by 4 pi, means multiply the numerator and denominator both by 4 pi, we can write it as mu naught I R square over 2x cube multiplied by 4 pi whole divided by 4 pi. So on rearrangement we can write it as mu naught over 4 pi multiplied by 4 pi I R square over 2x cube. Okay, so mu naught over 4 pi, and 2 1 is 2, 2 2 is 4, so it will become 2 pi. Okay, we are rearranging here it I, and it is pi R square, and the lower term is x cube. Okay, as you know that this was the circular loop, O was the center, R was the radius, so its area is pi R square. So here we can replace pi R square by A. So mu naught over 4 pi 2 I A over x cube. So this is the magnetic field due to a circular current loop at distance x. Now if I write here the electric field due to a dipole, electric field due to a dipole at a point x, at a point P, which is separated at distance x from the center of the dipole, and x is large, very large in comparison of the size of the dipole, we can write electric field E as E vector A is equal to 1 over 4 pi epsilon naught 2 p over x cube, where p is the dipole moment of the dipole. P is the dipole moment of the dipole. Now, if you compare these two formulas, B and A, here B is the magnetic field, A is the electric field. Okay, mu 0 over 4 pi, this is the constant term. Here 1 over 4 pi epsilon naught is the constant term. 2ia over x cube, and this is the 2p over x cube, means magnetic field at point P, which is lying at distance x from the center of the loop, is same dependence on x as the electric field E depends on x, which is the separation of the point P from the dipole. So we can conclude here that a current loop behaves same as a dipole, So we have the topic current loop as a magnetic dipole. So we deal a current loop as a magnetic dipole. In electric field or in electrostatics, we have a dipole, simple dipole. Here we have a magnetic dipole, and this is represented as a circular current loop. Okay, now you can see here this term and this term are constant. X cube 2 means this quantity and this quantity should be analogous. So here this term Ia is called the magnetic moment, as P is the dipole moment. Okay, so it is written as M. This quantity, which is called the magnetic moment, is written as M vector is equal to Ia vector. M vector is equal to Ia vector, because here this is the dipole moment, which is a vector quantity. We have assumed that this quantity, which is called the magnetic moment, is a vector quantity, and it is given as Ia vector. Now from this expression you can relate that the direction of magnetic moment will be same as the direction of the area vector. So if we have the circular current loop as this one, and this is the center, and current is flowing anti-clockwise direction. Current is flowing anti-clockwise direction, means let us consider this is the circular loop and current is flowing in this way. Okay, so we will curl right hand's finger along the direction of the current, and the direction of thumb will represent the direction of the area vector and simultaneously the direction of the magnetic moment. Okay, I am repeating this. If the current is flowing anti-clockwise direction, we will curl our finger, right hand's finger, along the direction of the current, and the direction of thumb will represent the direction of the magnetic moment and the direction of the area vector. Basically, area vector is the vector that is the perpendicular to the plane of the loop. So this is the plane of the loop. Okay, and if we take this one, so this is the perpendicular to the loop, so it will represent the direction of the area vector of the loop. And you can see here from that when we curl our finger along the direction of the current, and the direction of the thumb is also perpendicular to the loop, so it will represent the direction of the magnetic moment and the direction of the area vector. So we can write it that this vector, that is n cap, is representing the direction of the magnetic moment. Let us consider we have the loop as this one and current is flowing clockwise direction. Current is flowing clockwise direction means, so now you can see here, let us consider this is the circular loop and current is flowing clockwise direction. So to determine the direction of the magnetic moment and the area vector, basically area vector की डायरेक्शन तो ऑब्वियसली परपेंडिकुलर होगी, बट हम किस डायरेक्शन में लेंगे? परपेंडिकुलर तो ऊपर भी हो सकता है और नीचे भी हो सकता है, तो इसको डिटरमाइन करने के लिए हम राइट हैंड थंब रूल का यूज करेंगे. सो द डायरेक्शन ऑफ द मैग्नेटिक मोमेंट can be determined by using right hand thumb rule, and for this we will curl the finger of right hand along the direction of the electric current, and the direction of thumb will represent the direction of the magnetic moment. So current is flowing clockwise direction in this one, so we will curl our finger, right hand's finger, along the direction of the current, and the direction of thumb, that is the lower direction, will represent the direction of the magnetic moment. In the previous case we have the direction in upward direction, now we have the direction in lower direction. So the direction of magnetic moment will be this one. Okay, so this is the magnetic moment. Here, if the number of turns in a circular loop, as you can see that a circular loop can contain so many turns. So if number of turns is n, number of turns in loop, then magnetic moment m will become n times of Ia. This will affect only on the magnitude of the magnetic moment and not on the direction of the magnetic moment. So this is the m vector is equal to Nia vector. Okay, now the SI unit of the magnetic moment, as m is equal to Nia, so I ampere and this is the area, so ampere meter square. This is the SI unit of the magnetic moment. Now its dimension will be, for area, that is the L square, and sorry, this is the ampere, this is ampere, so for ampere this is the A, and for meter square it will be the L square. So this is the dimension of the magnetic moment. So thank you for it.